Hello and welcome to this next lecture on acoustics. We were looking at the solutions for a pulsating sphere, and last class we started looking at the ratio of the pressure to particle velocity known as the acoustic impedance ZA, and we will continue from there. So, if we take a look at this Z tilde A, okay. So, what do we have? Time is anyway cancelled. This exponent is also cancelled, so I will not bother about it. So, what we get here is j omega rho 0 q by 4 pi r into 1 plus j k a. And from the other side I get q by 1 plus j k a 1 plus j k r by 1 plus j k a. Hope all is correct. So, this goes away. Oh, there is something wrong, hold on. 1 plus j k a by 4 pi r square, 4 pi r square. Okay. So, this j k 1 plus j k goes with that, and then I have 4 pi goes with 4 pi. Okay. So, I have an r in the numerator, q goes with q, I have j omega rho 0 r in the numerator divided by 1 plus j k r, and this I will divide by c, multiply by c, and this I will take it as k. So, I have j rho 0 c k r by 1 plus j k r. Okay. So, last time we said we have already seen what is mechanical impedance, and now we are seeing what is acoustical impedance or acoustic impedance. They are not very different. Okay. Mechanical impedance divided by one cross sectional area dimensionally becomes acoustical impedance, and its characteristics are the same as that of mechanical impedance. Okay. It is typically complex, real part, imaginary part. Imaginary part is indicative of resonances, everything is same, okay, except that it has a cross section area division from mechanical impedance. Okay. So, this is, so my Z A tilde is j rho 0 c k r by 1 plus j k r. Okay. So, now I have a source of some radius a, and I have this distance r somewhere, and I am looking at the acoustic impedance on that surface. Okay. Now, if k r is much greater than 1, if suppose k r is much greater than 1, okay, then my Z tilde A becomes j rho 0 c k r by j k r. Okay. Between 1 plus j k r is big, so I am going to ignore this 1. Okay. So, this j cancels and I get rho 0 c, it is a real number. Okay. And what did we say, when it is real number, there is dissipation or power consumed. okay, this dissipation or power consumed. And why is that? The reason is that as we go far and far, okay, the spherical wave, the spherically symmetric wave, approaches a plane wave. Okay, and in a plane wave, the pressure and particle velocity, if this is the pressure, in a plane wave, particle velocity u is a tilde by rho c or rho 0 c. So they are in phase. Pressure and particle velocity are in phase. Okay, and so the impedance is real, right? A tilde by rho 0 c is equal to rho 0 c, which is the characteristic impedance of the medium. Okay, so this is the ZA in the plane wave case. Okay, so now as Kr becomes bigger and bigger, we are approaching the plane wave case, and so the acoustic impedance becomes real and power transfer is efficient. Okay. On the other hand, this is also the reason why the particle velocity in the monopole, is proportional to pressure in the far field. Same reason. Okay, the waves are becoming planar, and so just as in the plane waves, particle velocity and pressure are in phase. Okay, just a tilde by a real constant is particle velocity and a tilde is pressure, so they are proportional. So the same thing happens in the case of monopole also in the far field. Okay, the particle velocity and pressure are in phase. That is reflected by the acoustic impedance, which becomes real. There is a exact one-to-one correspondence. Okay, now on the flip side, so let me take this expression with me. On the flip side, if Kr is much smaller than 1, okay, that means I have a Ka which has to be smaller than 1, and then Kr is smaller than 1. Okay, so this is A and this is R, smaller than 1. Then what happens? Then here I ignore Jk R in place of 1, so that my Z tilde A is approximately J rho 0 C Kr. It is imaginary. Okay, so if it is imaginary, if the impedance is imaginary, that means what we should know, that typically these are supposed to have a real part and an imaginary part. Real part indicates dissipation and power transmission, whereas this is indicative of non-dissipative aspects such as stiffness and inertia. Okay, so now with Ka being small, so that Kr can also be very small, that means we are actually in the monopole region. regime, what happens is that the impedance looks imaginary, largely imaginary, dominantly imaginary. Okay. There is a small component of real, maybe we are approximating, but it is dominantly imaginary. Okay. So, power transfer or power radiation is difficult. Radiation is difficult. In other words, the source is a poor radiator, Okay. Now, just as ZML, the mechanical impedance ZA, okay, is indicative of the nature of the medium. Okay. So, now if we specialize this to the surface, okay, of the sphere, then what we get is J rho 0 C K A by 1 plus J K A. Okay. So, now if K A is small, then my Z A is imaginary. Okay. If K A is small, it is a monopole. Okay. And the monopole says that at my surface, what is it saying? At the surface of the monopole, the medium looks like an imaginary impedance. Okay. And so, no power transfer, no transfer of power. I am not able to transfer power, okay, is what it says, no transfer of power. That means an inefficient radiator. Okay. If you recall, the mechanical power was given by force squared by 2 magnitude of mechanical impedance squared into the real part of the impedance. Okay. If there is no real part over here, there is no time averaged power transfer. This was the expression for averaged power transfer. So, on an average in one cycle, the monopole is unable to transfer power. Okay. There will be instantaneous power transfer, instantaneously instantaneous power transfer occurs between the monopole and the surrounding medium is there, but that is positive and negative, that goes positive sometime and negative sometime. That means the monopole radiates part of the time and it takes it back part of the time. So, on an average there is no power transfer. Okay. All these are tied together, all these ideas, Ka being small, the radiator being inefficient, at the surface of the radiator the acoustic impedance being purely imaginary being, if you calculate the average power, it is going to be 0 because of this reason. Okay. All these are tied together. So, small Ka, typically low frequencies and small dimension radiators are inefficient radiators. On their surface the rest of the medium presents an imaginary acoustical impedance, and so they find it difficult to radiate sound efficiently. Okay. Whereas on the other hand, from the same expression, if Ka becomes larger, that means either a frequency goes up, okay, or the dimension goes up, source dimension goes up. Okay. Why frequency goes up? Because K goes up. If K goes up, omega goes up, because K is omega by C. So, either omega goes up or A goes up. In this expression you can see in the denominator Ka is much bigger. So, my Z acoustic becomes equal to J by JKA. J cancels and you see this is the acoustic impedance of actually a tube, a plane wave. You know, if I have a tube and a piston is driving the air within the tube, you will get an impedance of rho 0 C, which is the plane wave acoustic impedance. Okay. And it is real. So, as my size of the radiator becomes big, okay, as the Helmholtz number becomes big, then we approach plane waves. Okay. That is also imaginable. You know, if I have a bigger and bigger and bigger source. Okay. So, locally now I am straight line. Okay. The earth looks like a flat surface. Why? Because it is huge radius. Okay. So, this region looks flat. So, the system starts to behave like plane waves. So, we get the impedance that the plane waves have, which is a real number. Okay. So, now let us calculate the intensity, sound intensity. Sound intensity. Okay. If we look at the sound intensity, intensity is just like power. Power was given by 1/2 the real part of F into V conjugate. Okay. Intensity is power over unit area. Okay. So, if this area is taken in, then this becomes pressure. Okay. So, sound intensity, okay, or average sound intensity is given by 1/2 real part of P tilde U tilde conjugate. Okay. So, if we now look at that, let us see, we have 1/2 the real part of P tilde is j omega rho q by 4 pi r e to the power of minus j k r minus a by 1 plus jka into u conjugate, which is q by 4 pi r square 1 minus jkr by 1 minus jka e to the power jkr minus a. Okay. So now let us see what happens here. So this goes anyway, this part goes away anyway. Okay. Yeah, this part goes away. And so now we have 1/2 the real part of q square by 4 pi square r cube, okay, j omega rho into 1 minus jkr by 1 plus k square a square. Okay. So now you can see that because we are going to take the real part, for time average intensity, okay, this part that was there 1 minus jkr over r square, okay, 1 minus this was the key factor in particle velocity. There of course it was plus jkr, here because of the power expression we have to take minus jkr, okay, but this part is coming from the near field, 1 by r square is coming from the near field, whereas jk over r is coming from the far field. Okay. So now in choosing the real, what happens is that the near field is not chosen. So the whatever averaged power due to near field components is 0. Okay, average near field components is 0, whereas the far field is accounted for. This and this, the j and the j give j square, which is a real number. Then when I choose the real, that gets chosen. So the far field value, okay, so the far field components give non-zero power. Okay. What this is just saying is that one should not try to measure average power in the near field of a source, okay, because the particle velocity will be dominated by 1 over r square, which is 90 degrees out of phase with pressure, and the 1 over r is submerged because R is small, this will dominate. So 1 over R is buried in your measurement, so you will have an error. Okay. So if you are trying to measure average power, you should be in the far field. That is what this says. Okay. So now if we look at the power expression, this is 1/2 q square omega rho 0 by 4 pi whole square r square k over 1 plus k square a square. Okay. So this can be put in much nicer terms. Maybe I should do that, or we'll just leave it at this. Okay. Now what is the idea you should take away after so much? Okay. One is that if Ka is much bigger than 1, the acoustic impedance is real and the source sees a real impedance. The pulsating sphere sees a real impedance and sound radiation is efficient. Okay. Whereas if Ka is much smaller than 1, then either the size is small or the frequency is small, then Za presented by the medium to the radiator is largely imaginary. Okay. So the source sees an impedance that is imaginary and is unable to radiate. So the sound source is now inefficient. Sound radiation is inefficient, sound source is inefficient. That is one thing you take away from this. The other is with regard to measurement. Okay. The other is with regard to measurement. Whatever be the source may be small or large. If you are close to the source, so here we spoke about K times A, okay, the source dimension which is A. Here we talk about R, okay, close to the source, closeness to the proximity to the source is in terms of K times R. Okay. Of course, if Kr is much greater than 1, it does not matter what Ka is. Okay. You are outside the source, Ka can be small or big, but if Kr is much smaller than 1, then Ka has to be much smaller than 1. There is no choice. Okay. So if Kr is much greater than 1, then you are in the far field, and what you will be left with is a particle velocity that is in phase with pressure, and you get accurate measurements. Whereas if Kr is much smaller than 1, or you are approaching the near field, then U is 90 degrees out of phase. With pressure. Okay. And so measurements will be inaccurate. Measurements inaccurate. So one is about the source being big or small, and how it views the medium, and how the impedance at its surface turns out to be. This is the impedance, acoustic impedance at its surface, and how it sees the rest of the medium. If it sees it as real, that means it is able to radiate sound. If it sees it imaginary, it is an inefficient radiator. The other is whatever be the dimension of the source, whether should you be in the far field of the source or near field of the source. Okay. So now we saw here, okay, we saw here this we saw this here, this acoustic impedance. So let me carry it. Okay, this is the acoustic impedance. Okay, and if we specialize it, if we make it mechanical, first of all let's make it mechanical. So I just multiply by the surface area. Okay, so J rho 0 C, the surface area, which is 4 pi r square k r by 1 plus j k r. Okay, and this is S. This is S. I can take S, sorry. Okay, so if kr is much greater than 1, okay, then I have jkr here, kr here. This approaches rho 0 cs, a real number. We have seen these expressions in strings and rods. Okay, the impedance is, whenever there is a real impedance, it radiates or power is transmitted. In case of infinite strings or infinite rods, okay, we saw the mechanical impedance was rho 0 cs, so power is transmitted. Okay, so you should be in the far field. This is far field. Contrast kr, you are much less than 1. Okay, what you will see is a j rho c k r. It's an imaginary mechanical impedance. Okay, so the mechanical impedance is imaginary, no power is transferred by the source. Okay, that's one aspect. The more interesting, if we specialize it now to the surface, okay, specialize the mechanical impedance to a surface, what we get is J rho C, okay, just hold on. I have Z A tilde is equal to J rho 0 C K A by 1 plus J K A. Okay, and I multiply by the surface area 4 pi a square. Okay, that makes it mechanical impedance. Okay, now if Ka becomes small, okay, so this ends up looking like a J rho 0 C K A into 4 pi a square. Okay, in the denominator I have dropped the Ka, numerator Ka stays. Now this is 4 pi a cube, so I write this as J rho 0 C K into thrice 4/3 pi a cube. This is the volume of the sphere. Now the small sphere, and this is 3 times the volume, so it's 3v0 into rho 0 is 3 times the mass, 3 times the mass, and this is omega, k times c is omega. Okay, so this is what I have, J, I have omega, and 3 times the mass of air, whose volume is that of the sphere. Okay, you take the sphere volume and the mass of air in thrice that volume. Okay, so what do we mean by this at the surface? So that means this small monopole is seeing the rest of the universe as a 3 times the mass, okay, of a volume of air that is enclosed by the sphere. The whole universe is looking like a mass, okay, and mass is not a dissipative element, not a dissipative element. Only a damper is a dissipative element, okay, not even a spring is a dissipative element. So this universe looks like a mass to this small monopole, and so it can't radiate sound. It's an inefficient radiator. On the other hand, if Ka becomes big, okay, that means the radiator itself is now becoming bigger and bigger. Of course, it is approaching the plane wave situation. So we get rho 0 c, Za tilde or Zm. We are interested in mechanical impedance. It is rho 0 c into the surface area. Okay. So that's pulsating sphere, your first source, pulsating sphere. Okay, and it is uniform, so it has no theta phi dependence, no theta, no phi dependence. Okay, the pressure just decays away as 1 over r from the surface. Okay, 1 over r decay from the surface or from the center. Okay, and no dependence or theta or phi, no dependence. Okay, I will stop this lecture here and we will continue along these lines.